participants, and one of the things that's great about it is it kind of reinvents itself from time to time, makes new opportunities, and connects people doing experiments, people doing observations, people doing theory, and people doing simulation. And so that's a good thing to do. So, for some reason this isn't working. Okay, so I saw the title of the session here, which is about this spectacular paper, world game-changing paper about dark matter at 41, I think it is, 41 years ago. So I thought I would talk about the dark matter telescope at 29. So what is the dark matter telescope? Well, Tony Tyson and, oh my goodness. Oh my God, it worked. That's fantastic. Given the way this is rigged, I'm surprised. So, Tony Tyson and friends back in the mid-90s realized that if you could make an engine for seeing large numbers of galaxies and measuring their shapes very well, that you could, by a weak lensing, reveal distributions of dark matter, which I know is something, you use the words galaxy and dark matter and your ears perk up. So he and a few other people came up with a design that's got a wide field of view, a large collecting area, and is very agile so that you could move quickly and revisit places many, many times, and therefore average down effects of atmospheric seeing and other things. That became, 10 years later, the Large Synoptic Survey Telescope. And then in 2019, in December, an act of Congress renamed that to be the Vera C. Rubin Observatory. And so this is really my talk, a very brief introduction to the Vera C. Rubin Observatory. So what are all these terms? It used to be called the Large Synoptic Survey Telescope. You see everything. Then, as I said, it was renamed in honor of Vera Rubin. Lots of connections between even people here in this room and Vera Rubin, and of course UC Santa Cruz in Vera Rubin. And you'll notice the two signatures here on that act of Congress in December of 2019. It involved both Nancy Pelosi and I can't really read. It's a hard signature to read. But it's really great that when President Trump and Speaker Pelosi agreed on something, that's, you feel really privileged to work on something like that. The word survey is not the kind of survey you get after you've taken your airplane trip. It's to look at the whole sky over and over again, and there's a 10-year survey, and we decided to call the data set the Legacy Survey of Space and Time, which just happened to have the same initials, LSST. And then you may see Charles Simone's name periodically because the telescope itself is dedicated to Charles Simone, and you all know about arc minutes and arc seconds. All right, so Rubin's superpower is that it does three things incredibly well all together. Some observatories do one or two of those things. We're able to do all of them, and that is that we can see broadly, deeply, and frequently. So we've got a large field of view. We can cover the whole sky. That means we drastically reduce observing and sampling biases. We don't have to fight with each other about where to look. There's no time allocation committee. There's no time when proposers have exclusive data rights. The data go out to people quickly. So that's very good. And to do that, you need a large field of view. And the observatory, including the camera, has a huge field of view. It's about 10 square degrees, a little less than that, 3.5 degrees in diameter. So the full moon is small on that scale. So that is spectacular, really important. And if you want to Nyquist sample the PSF, you want to not undersample the point spread function. It turns out you need 3 billion pixels on the screen. On the focal point. So The camera is a 3 gigapixel camera that has to be read out in just a couple of seconds. And so that was a challenge all by itself. And because of the very fast beam, in order to have a wide field of view, the whole focal plane has to be flat to plus or minus 11 microns. None of this was easy to do. The camera actually has several superlatives. It's got a few Guinness Book of World records, and so that's really important. You want to be able to have a large field of view. You want to be able to see deeply. In other words, you need a large collecting area. So it's 8-meter class primary mirror. The primary and tertiary mirror are integrated on the same structure, which was also pretty novel. So the result is that it's really the equivalent of about 6.5-meter primary mirror. It's still really great. That means that in a short amount of time you can see quite deeply. Why is that useful? Well, we knew all along this was going to be useful, but here's a very good illustration from Sloan Digital Sky Survey. If you can see down to about 22 and a half in R band, then you get to see this kind of amount of structure. But then if you can go to 27th magnitude, and even on this projector, okay, even on this projector you can see what you get to learn, and most of those things are galaxies, of course. And this, great, thanks, Joel. And this is, just to give you a sense, this is of an area equivalent to 1/16 of one Rubin camera CCD, and there are 189 CCDs. In other words, this is 1/3000th of the field of view of the observatory. And of course, we don't get to 27th magnitude in a single visit, but we certainly do over the survey. And so you can see the huge advance of that. To do that, you need a large mirror. And then you want to be able to go back to various parts of the sky over and over again. One reason for that is because we wanted to open the time domain. Somebody opened their speaker. That's fine. Any good professor likes feedback, so thank you. You can kick me off now if you want. Okay, so one of the things you can do, if you go back and visit a place many times, you can average down atmospheric effects, because unfortunately nobody's figured out yet how to do adaptive optics on a 10 square degree field of view. That would be really interesting, actually. But of course, also you can see how things change over time. So opening the time domain is a huge deal. We'll revisit every object 800 times. And to do that, you need also an agile observatory. And so here is the observatory. It's in Chile, right kind of in the middle, north-south. La Serena is the closest city. And La Serena looks a lot like Santa Cruz, actually, in many ways, both in terms of climate and even this bay here. I'm not going to have time to go into the science that we think we're going to be able to do. My main points here are that one data set serves many science topics, and that means that lots of different areas of astronomy and astrophysics, and even particle physics, will all be fed by this spectacular data set. And we'll have roughly 17 billion individual stars and 20 billion galaxies visited 800 times. And bringing all of these people, different people with different traditions together, is absolutely spectacular. You can't just do this. It was really hard to do. I already told you about the camera. It's huge. It's very massive as well. And it sits up here on this big and agile telescope. Here's where M1, M3 goes. M2 is here, and the camera is here. I have some videos of what that's like if you're interested. And then just reducing the data is a big, big deal. We make about 10 terabytes of data every single night, and that has to be processed, and that means that the software was part of the construction project. Just very quickly, this is a quick summary of the high-level requirements. There are 6 bands, U, G, R, I, Z, and Y. These are broadband filters inspired by Sloan, really, and this gives you the single visit limiting magnitude depth, and you get to see each of those objects 800 times distributed over the 6 bands. And the way in which we're going to observe, the way the survey is conducted, is the result of a 10-year process with the community for how to optimize that survey. And I don't have time to go into that, but if you're interested, I can tell you. It's a ground-based observatory, of course. What matters here really is the requirement that the system adds at most 0.4 arc seconds to the delivered image quality, and then if you convolve that with the natural seeing on the summit, typically it's going to be about 0.7 arc seconds. Okay, so we in June, very recently, had a first look event. Hopefully you all saw it, if we did our jobs right. This was mainly not a science release, but a kind of a release for the public to let everyone know that it's working. This happened a lot earlier than we originally planned. That's a good thing, but it was also harder for us. I'm not going to have time to show you everything that we released in first look, but I will show you some highlights, and you go to rubinobservatory.org. I just want to talk about co-authors. There are thousands of people who made this possible, but the group itself responsible for making the images involved me, Claire Higgs, and Jose Pinto from the Education Public Outreach Group, some really great experts in making astronomical images for the public at Noir Lab. Keith Bechtel and Robert Lupton are colleagues on Rubin commissioning, and Nate Luss and Lauren MacArthur are part of the data management and are real experts in making images as well. And there were a large number of other people who also made various pieces of it. So the one I think will interest you the most is around M49. There's this gorgeous image, which I hope you've seen on the web. The projector's good, but it doesn't, we've lost a couple of magnitudes of depth here. It's even deeper than this if you look on your screen. And I love this part of the field because it looks like a collage that you've almost just pasted together of interesting galaxies, which is really great. The interesting thing here also is that this is about 2% of the field of view of the camera. In other words, every time you take an image, you see 50 times this area. So it gives you a sense of the throughput, the torrent of information that's coming out of the observatory. This is a cropped version of the full M49 field. This is about 16 square degrees. Again, you've lost a lot of depth and a lot of information. These images are huge. We processed about 2.5 trillion pixels of sky information in order to make this, and this cropped version is just a rectangular version of it. The whole field is about 24 square degrees. This is just the part that you saw in the previous slide. So you get a sense, again, of scale. This is a little less. This is just a little more than one. It was really two camera fields of view that were that we used to look in this region. The thing you should know is that this corresponds to something about 5-year depth. There are 1,185 individual visits that were co-added in order to make these images. And we understood that for the public, we really needed something that was interactive, that you couldn't just look at a zoomed out image because there's no way any screen or any person could see this very well. And so this gives you a sense, just walking around the 24 square degree field, just a huge variety of objects. Pay no attention to the slight over subtraction of backgrounds around the biggest galaxies. We worked very hard on that, but there's obviously more work to do. We think the smaller scale features are good, though. And this is the full 24 square degrees, so and there's the camera field of view. And then, of course, we start our sky survey and start filling in the whole thing. Let's see, how much time do I have, Joel? Looks like I have 0 minutes. Okay. So you know what? I will just recommend that you look at rubinobservatory.org for lots of things, more things. These are not satellites. These are asteroids that move from visit to visit, each one in a different band. And so you can see them and turn them on and off. We have this tool called Skyviewer where you can yourself, if you go to skyviewer.app, grab the full field, turn on and off the asteroids, but also look at all the galaxies. It's incredibly enjoyable to look at it. We've discovered a huge number of asteroids in that field as well, and we had lots of great coverage in the media, lots of watch parties. I just recommend if you ever get a chance to have your image on a Jumbotron, your astronomical image, go for it. It's just, there's some pleasure in just seeing that. That's just fantastic. So the data will feed lots of different science areas. There are 8 international science collaborations all ready to go. You've probably stopped reading after the first one, Galaxies Science Collaboration. You'll hear from Brant Robertson, if he isn't here already. He's the was the co-chair of that group, and he'll be talking in a later session. There are a lot of us also involved in the Dark Energy Science Collaboration and very interested in transient. The data are, we bring scientists to the data instead of sending the data out to scientists, and if you go to rsp.lssp.io, you'll get lots of information. I just want to finish by saying we released on June 30th Data Preview 1, which was from the commissioning camera, which you could argue is a big camera or also a small camera. It's got about a half a square degree field of view. It's 1/21st of the full focal plane. That's still pretty fantastic at full depth. And so we released those data from a campaign in November and part of December and at the end of October. And there's already a lot of analyses already appearing on the web, which is just so great. And then last week I was at our Rubin Community Workshop. I just got back. And, you know, you can write down all of the parameters describing this incredible observatory. But what's amazing is when you see the kind of torrent of information and results and people grabbing the data and doing all kinds of interesting things with it, even with just the earliest commissioning engineering data, it's just very exciting. And I'll commend you to just a couple of things. One is a great talk by Anja van der Linden and many other people in DESC. Just one of the fields included galaxy cluster, and so you could check for weak lensing with Rubin. And in fact, the message here isn't that our image quality is spectacular, because it isn't yet. We still got months of commissioning work to do. But what we do have is our understanding of the points of intersection and an ability to calibrate and already recover a weak lensing signal, which is really great even for this earliest commissioning data. And because we observed so frequently that field around M49 with lots of asteroids, people could use that to search for tumbling asteroids. And of course, your eye is drawn to the bigger asteroids, because everyone does. But what's interesting is that with a large collecting area, you can see the dimmer stuff as well. And you can see that we've got things that are the fastest spinning asteroids ever, and that helps to understand composition. How does it hang together? Which is interesting as well. So this is something that Sarah Greenstreet and Mario Jurich talked about just a couple of days ago, and there's a paper on that. And anyone here from Harvard? Okay, I can talk about this then. No, I'm just kidding, sorry. Of course, you all know about 3i Atlas, and so there were data with LSST-CAM, the big camera, so that was also a new paper that is on the archive and was submitted and is undergoing some revision. So that's great. I will now finish. What's next? We got a lot of work to do still. Don't be fooled, please, by the spectacular, I think spectacular, first look images. Those were co-ads of lots of visits. We have a lot of work to do in making the system work reliably. We have great image quality some of the time, but we have to have the active optics system working under all conditions, and particularly under the relentless survey, which is quite a challenge. And we're on it. It's getting there, but there's still a lot of work to do. We've pretty much delivered what we've promised throughout the whole commissioning period, and we should be starting the survey in October. So I'll finish here with a great picture of Vera Rubin, and I really like both of these quotes, which you could read for yourself. But I will say here for this workshop, both of these are really important, but the idea here is not to redo stuff people have done before but better, but to have completely new ways of thinking about the data and using the data. And I think workshops like this make new ideas, and can't wait to hear them. Thanks very much.